Hello everyone, welcome back to the channel. So in the last video we learned like how we can convert token embeddings to true word embeddings. If you haven't seen it, check that out because that is the main important concept for token classification using pre-trained language models. Um, and in this video we will create a toy model for token classification, but before that, let us try to explore like what are the possible approaches that are there in literature. Okay, so there are three possible approaches that can be used for token classification using pre-trained language models. So first one is this feature-based approach where we add a simple classification layer on top of our pre-trained language model, and we simply fine-tune or train this classification layer only. We don't touch this pre-trained language model weights. Okay, that is known as feature-based approach. And the second one is fine tuning approach where we actually fine tune the pre-trained language model with the task specific layer. So here we are talking about token classification. So this will be a token classification layer, and then we have this language model, pre-trained language model. Okay, and the next one is a partial fine tuning where we only fine tune some of the layers and the classification layer. Okay, and for this tutorial we will only focus on this feature based approach. And if you want to learn about these two approaches, let me know in the comment. I will create a separate video on these. So let's dive in and check out like how we can implement our feature based approach for token classification using pre-trained language models. Okay, so let us go to our IDE. So here, so I already created a sample data. So here I have labels for these tokens. So each word correspond to these tokens. Okay. So for example, quick is a property, brown is a property, fox is an animal, and so on. So these are manually, I manually annotated them. But when we have a task, like for example, named entity recognition task, there you will have a data set which will contain like text and corresponding labels. Okay, and then you can simply convert the data into these into this format and then simply use the script as it is. So in the process, first step is to convert these labels into IDs. Okay, so let us do that first. So let us create a simple function and call it get label to idx vocab. Okay, and what we will pass here is simply data. And let us define our empty dictionary. Say let us say labels to idx equal to empty dictionary, and simply iterate over all the data that we have and simply create labels corresponding index. Okay, so we can simply iterate over all the data. So let us say for line in data, and let us say for L in line. So if L not in idx labels to idx, simply create labels to idx L is equal to idx. So create another variable here, idx is equal to 0, and simply we increment idx plus is equal to 1 and simply return label to idx. So this will give us a dictionary that will that will contain a label and corresponding IDs. Okay, so let us run it with the given labels. So let us say labels to idx is equal to get and simply pass labels. Okay, and let us print it. Print labels to idx and simply terminate the code. So let us run and see it. So you see, it has O corresponds to 0, properties corresponding ID is 1, and animal has the ID 2. Okay. Let us create one more dictionary like reverse order, so where it will contain id to labels. Okay, so let us say idx to labels is equal to, simply what we can do is we can simply say for key in labels to idx, and what we will do is instead of arranging it in key and value order, we simply reverse the order. Okay, so now it will be other way around. So now here we are saying that um, key becomes value and value becomes key. So this is key which is now value, and this is value which is now key. So it is like idx to label. So we can print and see it, print idx to label. Okay, so let us run and see it. So you see now this is id and the corresponding label and so on. Okay, and next we need to convert the whole data into id. So let us create another function that let us call it get define get labels to idx. Okay, and what we need is data and labels and the dictionary, okay, that has the label to id mapping. Okay, and let us say we have another list there where we will collect all the data. So let us say uh, labels ids is equal to empty dictionary, and let us iterate over all the data. So for line in data, and then for l in line, simply what we will do is we will simply say here we need to create another empty list, label ids, call it label id is equal to empty dictionary empty list, and we can simply append it. Okay, dot append labels to idx dot get l, and if it is um, not there, so we can simply say 0. Okay, that correspond to the o, and then simply return. We can say Anka as well if we define it, but for the sake of simplicity we don't use that here. So we can simply return this as a output. Okay, now let us call that function and see what we get. And let us say we have updated labels is equal to get labels to idx, and let us call it as positional argument labels and labels to idx, and let us print labels. Okay, and let us exit. Let us run and see it. We need to append labels dot append these label IDs. Okay, now let us run and see it. So you see we have IDs now instead of string labels. Okay, so this is the part of pre-processing with labels. Now let us implement our classifier. Okay, so let us create a class. So class classifier, and for PyTorch you need to extend NN module. Let us import it. Define init. What we need is embedding dimension, and we need num labels, and we need dropout. Okay, and let us call super, and let us say self dot embedding dimension is equal to embedding dimension self dot num labels is equal to num labels, and self dot tp is equal to dropout. Now let us create a simple MLP layer. Simply let us say self dot nn is equal to nn dot linear, and what it needs is simply embedding dimension, and the output should be num labels. Okay, and let us create another layer which is called dropout. So simply we can say dropout is equal to nn dot dropout, and we can simply say drop self dot dropout. Okay, self dot db, or we can simply say dropout. Okay, now let us create our forward method. Simply define forward, and what we will get is, say, let us say x, and let us first let us pass it through the dropout layer, and let us call the output to tensor is equal to self dot dropout, and then let us pass it through the linear layer simply. So let us call it again tensor is equal to self dot nn, sorry, let us say self dot ff instead of nn, and let us pass tensor to it. Next thing here, we need to convert it into likely for token classification. We need to convert the labels into a flat tensor so that we can use directly the cross entropy function that we get from the uh, torch library. Okay, so let us simply say tensor is equal to tensor dot view, and let us say -1 and self dot labels. Now simply return the tensor, and this is our model actually. Okay, so this is our classification layer that we have seen in our uh, presentation. So here, this is the layer that we implemented here. Okay, now let us create an instance of it and train it simply. So let us remove the comments. So here we have sentence embeddings, so which we have seen, and now let us create the model. So let us say model is equal to classifier, and what we need is embedding dimension is equal to 768, and num labels is equal to length of labels to idx, and simply let us say we use dropout is equal to 0.0. Okay, now let us create our loss function. So let us say loss function is equal to nn dot cross entropy, and let us define our optimizer is equal to optim dot, let us use adaptive momentum and simply pass model dot parameters. Okay, now this is our setup for model. So this is our model, and this is our loss function, and this is our optimizer. And let us say create our training loop then. Okay, so for training loop we simply say for e in range. So let us say we want to create like train it for 50 epochs because we don't have enough data, and let us say for label, let us say for embedding and label in zip. So we can simply say sentence embeddings and labels. Okay. And now as embeddings we get, they are tensors. So we can simply pass it to the model. So let us say, first let us zero grade the optimizer. So optimizer dot zero grade, and then we can simply say model output is equal to model, and we can simply pass the embeddings. Okay, and simply we can say loss is equal to loss function. So here labels are simply Python list, so we need to convert them into a tensor. So we can simply say label is equal to torch dot long tensor. Simply we can simply say label. Okay, now this is tensor as well. Now we can pass here the model output, which is a flat tensor, and we can convert the label in the same format as we have the model output. Okay, we can simply say -1, that will do the job, and then simply we call loss dot backward, so that will compute the gradient, and then we simply call optimizer dot step. Okay, that will update the parameters, and we will have the training completed. Okay, and then simply let us create another variable where we accumulate the loss. So let us say total loss is equal to 0, and we simply say total loss plus loss dot return, because it's clear scalar, so we can simply get it and simply print total loss. Okay, now let us run and see our training. Let us format the code and let us run and see it. Okay, so you see here it is started from 3.9 3.07 and just keep decreasing the loss. Okay, okay, next let us update our model to get a probability distribution over all the labels instead of just logit values. So we can simply say logits is equal to, we can simply say torch dot, let us use softmax simply, and let us pass the tensor, and let us say dimension is equal to -1, and let us return logits as well. Okay, so this will have the probability distribution of all the labels given a single token. Okay, and then we will simply run an argmax on dimension 0, that will give us like which particular label correspond to the token. Okay, so let us do that here. So we can simply say with toss dot no grad, so that it won't compute the gradient, and simply we can copy the code from here and paste it here. We don't need to do this, we don't need to do this, and now we need to compute this part as well. Here we don't need this, so we can simply say underscore. Here we don't need first part, we need logits. Okay, so let us run argmax so that we can get prediction is equal to torch dot argmax, and we simply pass logits here, and we can simply say dimension is equal to this one. Okay, and now let us print predict So, and also let us print labels like how good it is being trained. We'll see like we can compare it simply. Okay. Okay. I think we have the implementation ready. Let us train and predict. Okay. So you see it is able to predict it very well. So 0, 1, 1, 2, 1, 2, and so on. Okay. So it works. Okay, so in this video, we will stop here. In the next video, we will train this model on some real data and see like how good it works. Okay, then thanks for watching. Bye bye. Take care. See you in the next.